In this lab, I used the GlowScript platform to estimate the mass of a black hole a star is orbiting and modeled and chose velocities for two orbiting objects around a star. The purpose of this lab is to see if mass can be predicted using the computer platform and to see a visual representation of how orbiting can change depending on initial velocity. Inevitably, the code showed that the black hole had a mass of about 9.3 times 10 to the 33 kilograms and that the velocity of the star increases as distance to the black hole decreases. In terms of models, I primarily use Newton's second law, definitions of physics concepts, and universal gravitation. The universal gravitation equation is that the magnitude of F is F equals G times big M small m over r squared, and it predicts the force of gravitation relative to the distance between the two objects. This is also the equation I used to estimate the mass, which I did by rearranging the equation where the larger mass is on the left side of the equation. Furthermore, I continued to use velocity and position update formula to predict future values within the loop with net force, initial velocity, and a time interval, which was 1 Earth day in seconds. Velocity update formula is derived from the momentum principle, which is F equals ma, and position update formula is based on the definition of velocity, which is change in position over time. For Lab Part 1, the initial velocities and trajectory of the star was determined by my Georgia Tech email address. Inside of the loop was the position and velocity update formula so that they would repeat for every value of delta t, which was 86,400 seconds. The system in this part is the star and the surroundings is the black hole. Then, using the given initial velocities and the time intervals, I found the change in momentum versus time, which is equal to the net force on the object. Since the net force in this system is only the gravitational force, it allowed me to estimate the mass using the universal gravitation equation. Using this method, the mass stayed pretty constant throughout the entirety of the loop, and possible sources of error and the fact that it changes throughout the loop could be due to rounding errors. For Lab Part 2, the masses and delta t were already determined. However, I had to find a velocity for the ship that would allow the star and the spaceship to orbit without crashing into each other or leaving the orbit. This velocity ended up being negative 0.84 times 10 to the 4 meters per second for the ship in X and 0.44 times 10 to the 5th meters per second for the ship in Y. This number was extremely specific and took a lot of trial and error, showing how delicate the relationship between orbited objects can be for them not to collide. I also had to use equations to find all of the gravitational forces on the spaceship, which I found by putting the universal gravitation equation into the loop to update as the positions changed throughout the orbit, in relation to the ship to the planet or the ship to the star. With the outputs of the code, I found that it showed clearly that velocity increases the closer that an orbiting object gets to the more massive object. I found it extremely interesting to see how both the parallel and the perpendicular parts of momentum grew as distance decreased. For discussion, net force and change in momentum are different because they are found using different things. Change in momentum has to do with velocity and is multiplied by a constant mass, while net force is the addition of various forces. However, in this example, net force is the sum of all forces acting on the object, which is just gravitational force as the objects are in space. However, change in momentum can show how the net forces affect the system and their velocities, like how an increase in Fg has a higher velocity in the system. What if there was a black hole in the system along with the star, planet, and spaceship? In this scenario, each of the objects in the system would have the gravitational force of the black hole working on them on top of the gravitational forces within each other. The planet and the spaceship would continue to orbit the star, but the entire system would also begin to orbit the black hole, as the black hole is the most massive object, in a similar way to the moon orbiting the Earth, but the Earth still orbiting the sun. To conclude, I was able to predict the mass of a spaceship using the concepts of universal gravitational motion. I was able to update the velocities and forces using initial velocity generated to me and got a mass of about 9.3 times 10 to the 33. Additionally, I had to choose initial velocities for a spaceship orbiting a star that would not cause a collision between it and a nearby planet, which ended up being a very specific number.